All right, now I want to take a look at this area problem in general. So again, I've got this function, whatever it looks like, y equals f of x. I have it defined on an interval from a to b. It might be defined other places, but my interest may only be from a to b. Okay. The idea is I want to take that interval now from a to b and subdivide it into n equal pieces. Oops, n equal subintervals. So here we go. All right. 1, 2, 3, 4, 5, n. So we're at n equal subintervals. The width of each subinterval I'm going to call delta x. Now I'm choosing to make them all the same. In the really general situation, you don't have to make them all the same. But let's make them all the same because that's reasonably easy to calculate. The total length of the interval from one end a to the other end b is b minus a. And if I divide that by n, well, that's the width of the subinterval. Now, what I want to do is I want to cut this into rectangles. And the thing is, for each subinterval, I need to decide how high to make the rectangle. Now, in the example I did with y equals x squared, I did it with right-hand endpoints and left-hand endpoints. Actually, you can choose any point in the middle. So I could, let's grab a different color to do my point choosing here. Let's grab red. So I could choose this point in the first interval, and that point in the second interval, and this point, oops, that's not this point in the third interval, and this point in the fourth, and maybe right in the middle in the fifth, and the right-hand endpoint for the sixth, and something. Each interval you get to choose the point. And I'm going to call this first one here x1 star. It's like the star x value in the first interval. And this one right here would be x2 star and x3 star and so on. All the way down to the last one, which would be xn star. So that's the point that I'm going to plug into the function to see how high I want that first subinterval to be. So that first rectangle is that tall. The second rectangle, I'm plugging this x value in. So I go up to here and pick that. I can choose randomly anywhere in there to pick these x values to plug in and to make these rectangles however high I want them. In this case, you don't necessarily know if the area you're calculating is going to be an overestimate or an underestimate because it's not necessarily immediately obvious. The way we were doing it before, by always picking right endpoints or left endpoints, it might have been more clear whether your estimate was too big or too low. But here you're just getting some estimate. Okay, so each rectangle now I can calculate the area. So the area here, why am I not having a pen? There we go. That's right. The area is approximately equal to the area of the first rectangle plus the second plus the third and so on. So the area of the first rectangle is the width of delta x, and the height is f with x1 star plugged in. Right? That height. Take this x, plug it in to figure out how high that is. Plug it into that function. Right? The second one, the width is, again, delta x. And the height is whatever the function value is when you plug this point in, x2 star. So f x2 star plus, and so on, all the way to the last one, which would be a width of delta x and a height of f of xn star. That's an estimate of the area. Now notice I say area in that nowhere did I ever label what the x and the y axes are, right? Is this measured in feet and whatever? I'm assuming in this calculation that that this is being measured in some unit of distance, and the y value, the y is also being measured in the same unit of distance. Um, in a subsequent video, we'll see it when they're different units, but uh, for now, just assume it's inches times inches or miles times miles, and you're getting area. Okay. Now, that's an estimate. If we want to actually get better and better estimates, we could probably do something like this. That the area is going to be equal to the limit as n goes to infinity of this sum. Now it turns out that as long as f is a continuous function, it can be proven that this limit does exist and that the area is equal to that. Okay. This we'll be working on over the next week or two, and being able to actually do this calculation with different functions, right? Finding different techniques for doing this calculation.